Hello everyone. In this video, we're going to be solving an exponential equation, a homemade exponential equation. Now, these equations are very easy to make. You can experiment with it definitely. And we're going to solve for x values. Let's get started. First of all, I do have something like 5 to the power x plus 1 and 2 to the power x plus 1. If these were multiplied or divided, then I could use the common exponent. But when they're subtracted or added, it's not going to help because we don't really have anything for a to the x minus b to the x, except if x is an integer. Most of the time, we can factor this, and a minus b is going to be one of the factors. So this can kind of be factored for certain situations, but do you think x is an integer? That would be a good question, right? And if x is not an integer, can it still be factored? Something to think about. Well, that's going to be problematic because think about it. If you have something like a to the power 5 and b to the power 5, obviously we can kind of break it down into a minus b and then a to the fourth plus a cubed b, so on and so forth. But if this exponent is not an integer, how are you going to keep track of these? Because the powers are supposed to go down one by one, so that needs to be an integer. So as is, this problem is very problematic. But we can make it a lot easier by a little quick manipulation. Bring the 5's together and bring the 2's together. All right? So when we do that, we're going to get something like this. Original equation 5 to the x plus 1 minus 2 to the x plus 1 equals 2 to the x minus 5 to the x. And then we can go ahead and bring the 5's together and bring the 2's together. And you know this is going to bug me forever, so let me fix that. Okay. And then we can go ahead and factor this. Now, the good thing about putting the 5's and 2's on separate sides is that we can make a common factor, or we can find and factor. So here, 5 to the x plus 1 is 5 to the x times 5. So 5 to the x is a common factor. If we take it out, we're going to get 5 plus 1. Nice. Same thing here, 2 to the x, take out. You're going to get 2 to the power 1 plus 1. Or just to write 2 because you already know what it is. Hopefully, right? Now, this is very helpful because 5 plus 1 is actually 6. And 2 plus 1 is equal to 3. And 3 goes into 6. So we can go ahead and cross cancel. By the way, we're going to find the real solution and we're going to be chasing the complex solutions, which is going to be interesting. So from here we get 6 times 5 to the x equals 3 times 2 to the x. Oh, did I say cross canceling? Yes. 3 goes into 6 2 times. We kind of got an interesting equation because we got another 2. So it's up to you. If you want, you can leave it like this, or you can divide both sides by 2 and change the power. But it's better to keep it as is because now 5 and 2 have the same exponent, right? Or yes, I mean 5 to the x and 2 to the x. So we can kind of bring them together. Let's divide both sides by 5 to the x. I had to think about it. These two cancel out, and we get 2 to the x over 5 to the x equals 2. Nice. Since we have a common exponent, we can kind of express this as 2 over 5 with a common with a base and a common exponent like this. And then we're going to use what we just used today, right? Natural logging both sides. You don't have to use natural logs. You can use any logs, but I'm going to use natural logs because they're so natural, healthy, right? So now bring the x to the front. X times ln 2 over 5 equals ln 2. And finally, by division, we can find the x values. X values or x value? Well, it looks like there's only one because these are constants and their ratio is also a constant. So x equals ln 2 over ln 2 over 5 is going to be the only real solution. So how do we find complex solutions? Let's go ahead and take a look, and then we're going to take a look at something else. So to find complex solutions, we need to complexify one of the sides. So remember, we had this expression right here, 2 over 5 to the x. That's we were kind of left off. Equals, what was it equal to? 2. Okay, right? Now, to complexify, why did I say only complexify the right-hand side? because in my opinion, you only need to complexify one side. Some people claim that you got to do on both sides and add the 2 pi or multiples of 2 pi to both sides, but that creates some extra roots that don't satisfy the original equation. In my opinion, I could be wrong. Correct me if I'm wrong, but I think we just complexify the right-hand side. And we're going to do that by multiplying by 1, but not just ordinary 1, a very special one, which is the complex version. And that is e to the power 2 pi n I. Why? Because if you think about it, 1 can actually be expressed as 1 comma 0 on the plane, and it's basically 1 unit from 0, which makes a 0 radian angle, or 0 degrees, whatever, but radians are better. Wait a minute, what do you mean by 0 radians? Couldn't it be 2 pi radians? Sure, it could be 4 pi radians. Any multiple of 2 pi will do. So that's what 2 pi n does. N is an integer, and 2 pi n just represents any multiple of 2 pi. All right, so if n is equal to 1, you're going to get e to the power 2 pi I, and that's actually equal to 1. If you use 4 pi I, it's still equal to 1. These are all equal, but they are actually different representations. Anyways, this doesn't mean 2 pi equals 4 pi, right? Well, they're kind of equal anyways. So here's what we're going to do then. We're going to natural log both sides. Now, the reason why I didn't have to use e on this side is because when I natural log, it's going to be the same thing. You could also write this as follows. You could write this as e to the power ln 2 over 5 to the x, and write this as e to the power x ln 2 over 5. And when you do the natural log, the power is going to come down, and you're going to get the exact same thing. Make sense? But let's go ahead and ln both sides here. That's going to do the job. And then we're going to ln a product. How do you ln a product? Well, it's just going to be the sum of 2 ln's. And first of all, bring this x to the front. And as you can see, we get the same thing. This is a real valued ln. And on the right-hand side, we're going to get ln 2 plus ln e to the power 2 pi ni. And as you know, this is just 2 pi ni because ln e is 1. So x times ln 2 over 5 equals ln 2 plus 2 pi ni. You can now go ahead and divide everything by ln 2 over 5, and that's going to give you the answer. Let's go ahead and do it. And now we're going to write it, a clean version. They're going to cancel out. X is going to be ln 2 over ln 2/5, which you can write as ln 2 minus ln 5, by the way, plus 2 pi n over ln 2 over 5. All of that is multiplied by I. So that's going to be the imaginary part, and we have the real part. Interesting. Now, so that will be the complex solutions, not complex solution. There are infinitely many for every integer value, obviously. But specifically, if n is equal to 0, we're going to get the real solutions, or solution, right? There's only one. If n is equal to 1, you're going to get x equals ln 2 over ln 2/5 plus 2 pi over ln 2 over 5, whatever that number is, evaluate that. So as you can see, the solutions are complex when they're written in a plus bi form. You can definitely do that. And the real part is always the real solution. Let's go ahead and take a look at what Wolfram Alpha gives us for the real solution. Yes, what they did was, unfortunately, they used log for ln. That's kind of like common practice sometimes. And then they put a minus sign because they wrote it as ln of 5/2 instead of 2/5. Makes sense? That brings a negative power. And this is the complex solutions, again expressed in a slightly different way. And I think this brings us to the end of this video. Thank you for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe, take care, and bye-bye.